I am Maxime Raynal, as many of you know. I'm a PhD student in a third-year PhD student in Nokia Bell Labs and Université de Grenoble, with my two supervisors, Marc-Olivier Buob, which everybody in Links knows, I guess, and Quénot, which is my academic supervisor in Grenoble. Today, I will present you one of the things I worked on during my PhD with Marc-Olivier and Georges. It's an algorithm called fAST, which is designed to infer regular expression from examples. So the outline is pretty straightforward. I will briefly introduce the subject and the motivations behind it. Then I will explicit the problem we are trying to solve, present you our proposal, the experiments, and I will conclude. So our problem is that unstructured data are everywhere. Really, they're ubiquitous. We find them everywhere in huge quantity, and they contain relevant information that we want to extract. The problem we have is usually we need to structure this data before we can extract any relevant information. So how do we do that? We need to be able to identify pattern so we can build filters that will recognize these patterns, and then we can define rules or actions associated to each. There are many use cases to this problem. In our case, it's mainly in information retrieval and in networking. Basically, in networking, whether you want to implement a set of filters for a firewall or automatize log parsing or this kind of thing, you will always be confronted to building patterns that can recognize things. And that's where we come to our problem. The problem is the grammar inference problem. We have a set of strings that we call examples, S. So here we will assume that S has three strings, ABC, 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 ABC. And from S, we want to build a regular expression that can recognize all the words of S. So there are always some trivial solutions, such as the regular expression which recognizes the words in S and nothing else. Or another trivial solution will be the solution, the regular expression that recognizes everything. These two trivial solutions will always work, but we are looking for something more subtle, something which can recognize S, but not everything, and on the other hand, which can generalize a bit what we're seeing in S, identify patterns. And we intuit that the good solution here is ABC plus, meaning a repetition of the sequence ABC, because that's what we see in S. So now let's dive deeper in this problem. Basically, we will make a sort of metaphor between a game during a TV show, which is called Le Compte est bon, and our grammar inference problem. In Le Compte est bon, you get given a target number, and you get given elements, along with the four arithmetic operators, plus, minus, multiplication, division. And using these operators along with these elements, you need to reach the target. So here we can build 219 by having 2 times 10 plus 7 times 8 plus 3, we get 219. So more formally, what is this game about? This game is about building what we call an abstract syntax tree. An abstract syntax tree is simply a tree which represents an expression. Here, an arithmetic expression. So in this game, we are trying to build an abstract syntax tree that produces the right target. And the grammar inference problem is very, very similar. We are just going to have to change the meaning and the operators. So our operators will operate on strings, not on numbers. So we have the concatenation, disjunction, and repetition operators. And basically, our problem is the same. We don't try to reach a target number. We have target examples that we need our abstract syntax tree to recognize. The elements we work with are not numbers. They are the characters of our alphabet. And in a similar way, we will use operations to build a language that recognizes all the examples in the target. And that is a bit the spirit of our algorithm. It's working around abstract syntax trees, these type of trees, at the language level. So now, why is it a difficult problem? Why is it more challenging than le comptable? First, obviously, integers are much easier to manipulate than languages. It's easier to manipulate a bunch of integers than to manipulate languages. Another reason is that there exist many solutions to our problem. Some of them are trivial, and we don't want any solution. We want the good solution. So we will need to define a metric that allows us to characterize what is a good solution, what is a better solution, what is a bad solution. And yeah, infinite set of words, as I said earlier, languages are much harder to manipulate. What about the state of the art? A problem we had with all the algorithms in the state of the art is that they make use of counterexamples. Counterexamples are examples that have to not be in the target language. So the same way the regular expression must recognize example, it must not recognize counterexamples. And counterexamples help a lot the inference process. Without counterexamples, the problem somehow gets harder. So if there's one thing that distinguishes us from the rest of the state of the art, it's mainly this point. We work with less information. So our proposal, fAST, fAST for find abstract syntax tree, because that's what we're going to look for and that's what we're going to find. As I said earlier, we need to be able to define what is a good regular expression from what is a bad one or a better one. So we use an objective function. This objective function will rate an abstract syntax tree, and it's going to be a trade-off between two values, one that we call shortness, which represents how short and how readable regular expression will be, and the other one, the accuracy. The accuracy represents how strict the language it represents is. The more accurate the language, the less words it recognizes. So to compute the shortness, it's simply the size of the tree. The accuracy computation is somehow more complex because we try to see how big an infinite subset of an infinite set, how big is it? So the computation is a bit more tricky, but we managed to represent how dense a language is. And using this objective function, we can now start looking for solutions, as we can say which is the best, which is the not best. The algorithm is a search algorithm, branch and bound-like. We work with a population of abstract syntax trees. We store them in a priority queue according to our objective function. And at each iteration, we will pop the most promising solution, the most promising AST. If it's a final solution, meaning if it matches all the examples, and if it's the best one we saw so far, we save it. If it's not a final solution, we process one more character of the examples and we mutate it. To mutate means to consume a character and to be locally modified. So that's our way of building solutions incrementally. We push these children, these mutants, into the priority queue, and we continue. So yeah, in practice, it's not only an abstract syntax tree. It's a tuple with the abstract syntax tree, the number of characters it has consumed already, and an arc that we call the active arc that represents somehow where we are at in the AST, because we're moving in the AST as we consume characters. So the mutations themselves, like the process of how we can consume, how can an abstract syntax tree consume a character, be locally modified, it's something which is a bit tricky to do in a short presentation, but I will try to give still an intuition. The mutation process acts in two steps. First, we apply preliminary mutations. A preliminary mutation will only install a unary node somewhere. It somehow allows to bounce. I will show you on drawings later. So we start with these preliminary mutations where we put unary nodes here and there. And there's a final mutation that will install a binary node and a leaf labeled by the characters we're consuming. So here is what it looks like. On the left side is our current partial solution before the mutation with an arc. So basically X and Y are entire subtrees, and we're considering an arc. And here is the pipe mutator. A pipe is a disjunction operator. We see that we introduce somewhere in the IST, like on the previous active arc, a binary node, a new leaf, and that the rest of the AST is unmodified. So we have a series of mutations that work in this manner. Here are the dot mutation, which are more complex because unlike the pipe, the dot is not commutative. And preliminary mutations, as I said, we only add a unary node. The idea is that it allows the algorithm to bounce in the tree. Before it was going up, with the preliminary mutation, it's allowed to go down and vice versa. And this set of mutations allow to build all the possible types of ASTs, but in a clever manner, because we consider the most promising one first, like in a branch and bound local search manner. So now for the experiments. Our experimental setup was pretty straightforward. We drew 300 random regular expression, size 4 to 12, on an alphabet of size 6. And for each of these regular expression, we drew up to 500 instances, sometimes less when there's less words in the language. And basically, we compare the randomly generated expression R to the inferred one R prime. So sometimes we don't find R prime. That rarely happens, but that happens. And when we find one, we want to compare the value with the objective function of what we inferred with the one from the baseline. And we have three situations: not as good, at least as good, and strictly better. And in this drawing, we can see in green, it is strictly better, and in orange, at least as good. On the x-axis is the time, meaning that within 1 second, we solve a bit more than 80% of the instances, at least as well as the baseline we had. And in 40 cases, we even improve the baseline. Like we find a regular expression that is equivalent, but is better according to our objective function. And then when we go towards 1 minute, which was our time limit, we see that 90% of the regular expression are solved at least as good as the baseline we had. So that's it. I presented you our new algorithm that we called fAST for regular language inference. What is nice with it is that it's the only proposal we know so far that works only with examples and without counterexamples. And it's also an anytime algorithm, meaning it will keep improving the results until it guarantees an optimal, but it's anytime. It can be interrupted at any moment. It will have a solution normally. And that our experimentation show that even with Python monothread implementation, it works reasonably efficiently. And something I didn't mention, but which is a real plus, we can define user pattern, such as integers, IP addresses, and all, to have the algorithm infer regular expression using also these patterns in the inference process. So thanks a lot for your attention. And if you have questions, I'll be happy to answer them.
Thank you.
Yeah, sorry.
Any questions in the room?
Yes, can I start? Maxime, can you go back to the algorithm itself, please? So yeah, before the mutations. Okay, so what I didn't have the time to get is so when you explore new ASTs and so on, do you ensure that the ASTs that you have already match all the examples that you have, or do you in the same time go through the examples to match more and more a greater and greater proportion of them? Do you see what I mean?
I'm not sure. So I don't need to check that an AST keeps recognizing examples. At least we don't need to check it often, because by construction, most of the time we just make sure by construction of the mutation that it will be backward compatible somehow.
Okay, yes, I see what you mean. And so at the very beginning, so put the AST recognizing the word sigma 0 into Q, where sigma is the first character of the first example of S. So at the very, very beginning, the ASTs that you have in your priority queue, they don't recognize all the examples, I guess.
Yeah, at the very beginning, there's only one AST, which is made of one single leaf. It's to initialize the algorithm.
Okay, so I'm not sure if I understand, but there is somehow a growing phase where somehow you go from ASTs that don't recognize the examples to the first time when you see an AST that recognizes all of them.
Yeah, basically an AST is these 4 values. I mean a solution.
Yeah.
So A is the AST and IJ represent the like where we are at in the example. Like it means we recognize the I first example
Okay.
and the if one only till the jth character. So a solution is built to recognize that many characters, but not more. And they grow incrementally. Like the solution will consume a character and evolve to create new solutions, which will be different AST and which will also increment the values of INJ accordingly.
Maxime, maybe you could give a simple example where you have a simple positive example ABC and you explain iteration by iteration what you have.
Yeah, maybe I even. I know where it is. Ah, yeah, here, good. So imagine that this is the tree we get at the end.
Yeah.
At the very beginning, all we have is bot and A.
Yeah.
I know what I can do. I can build it up. So at the start, we have only bot and A. And then we discover B. So one possibility, because our example is ABC. Let's say our example is, ABC, ABC. So we discover A, then we consume a B. So the modification of the AST will be to insert these nodes to create the ABC tree. And then we will discover C. And when we discover C, once more, we will mutate the tree. Add more nodes. So that's what the tree can look like after discovering ABC.
Okay.
And then if we discover A again, one of the possible mutations will be to have a plus here. And then on and on and on. But we will have built this ABC tree, ABC plus tree, not one node at a time, but 1 or 2 nodes at a time.
Okay, so if I understand well, so you iterate through the characters of your example, and when you reach the last character, you will have an AST that matches all the examples. So maybe I would call that the end of the growing phase of the algorithm, when you finally reach a solution of which you know that it is a solution to the problem. And my question was, after that first phase where you're sure that you have a solution, do you continue to try improving the AST in terms of the objective function, or do you say, okay, now the algorithm is finished and I can just respond?
No. The algorithm continues.
Okay.
So we decide how we want it to stop. We can tell it to stop once it's found a solution, or after some time, or upon interruption. But it will continue until it has considered a gigantic amount of possibilities.
So if I might say, my main mental picture would be then that you have this initial growing discovery phase, and then you have an improvement phase.
They're similar in the sense that they always keep growing small solutions into bigger ones.
Maybe you could come back to the algorithm and show that whenever you discover a new solution, you update the best solution found so far. And so when you decide to interrupt, you just return the best AST that you have found so far, that is denoted by A star. So if you prefer, you have growing phases. So you update in your priority queue many AST. At some point, some of them will reach the end of the set of positive examples.
Yes.
So they are candidate solutions.
Yeah.
They will, as they are candidate solution, either they improve the best candidate solution found so far, and if this is the case, you update A star to this new AST. Otherwise, it doesn't improve A star, and so you just ignore the solution, or you keep it for the record as you prefer. But this doesn't improve A star. And when you decide to interrupt your algorithm, because, for example, you decided that you have spent enough time, you return your A star.
Yeah, sure. I was just meaning that in the iterations here, it looks like each time you process the next character, but unless there is no next character.
Yeah, that's the idea. Like, or you process the next character, or there is no next character to process, so it's a final solution.
Other questions? Yeah.
Okay, so I just wanted to ask if, for example, you know that in your data, the words you are looking for, the size is bounded. How do you manage to find an expression that is going to take into account that the words are bounded? So, for example, in the example that you built at the beginning, that you built just before with ABC. What if you don't want ABC plus, but like something ABC to the power of K or something? How do you do that? Or is it a problem that you want to look at, or it's not even interesting?
So one way we do it is we can, there's a parameter alpha in our objective function. So that's one way to put more weight or less weight on each part of the trade-off between a short regular expression and an accurate regular expression. Otherwise, it's really difficult to know what will the user want somehow. So in this example, depending which value of alpha we give, we can obtain any of these three solutions. I mean, now this one will always be better, but at least than the last one. Because the first one is very accurate. It's very precise because it's a extremely strict language. It recognizes only 3 words. So it is the most accurate expression we can find. So we could have it be the best solution for high value or low value of alpha. And this one is very short, and it is accurate. And this one is very short, but it is not accurate at all. So we use the parameter alpha to decide what we want more, accuracy or shortness. I don't know if that was your question.
No, my question was more about, like, if you know that it's the second one that is more accurate between those three, what if you know that the size of your words is bounded, and so then you don't send ABC plus as a result, but maybe something like epsilon plus ABC to the power of k or something like that? Like, are you able to do that, or is it interesting to do that? I don't know.
It's not very adapted to regular expressions because the two operators plus and star, they immediately imply that that the language will be infinite. At least part of it will be unbounded.
I think it's not exactly the question, because indeed, in regular expression, you have an operator that allows to define a finite number of repetition, possibly a range of repetition, for example, from 3 repetition to 5 repetition. And so I guess that the question is more related to this kind of operators. And so if you would like to support this in fAST, you would have to introduce the corresponding mutators, which is not yet done, and which would be very complicated, because for the moment, when we introduce repetition operators, this is clearly defined what we want to insert, where, and when. If you want to start to introduce a repetition, do you want to start with 3 repetition, 4 repetition, 20 repetition? It would be very tricky. And so it would force you to update the bound of the range of repetition anytime you want. So you could imagine, I guess, to replace the plus operator and the stars operator by, say, a range operator, and updating progressively during the mutation those bounds. But we didn't work on this. But actually, it could be interesting. It could be an interesting improvement, because, for example, when you want to recognize IP addresses, you know that you have IPv4 addresses, you know that your number are between 0 and 255. So you know that you have basically packs of 3 integer digits. And so you'd like to bound each part of the IP address using this bound. So this could be interesting. But this is not solved by the algorithm. And you have to understand why we didn't do so. So first, this is very complicated to update the bound, but also just considering this set of operators is quite tricky to manage, because you have a terrible combinatorial explosion whenever you append a new character. Whenever you discover a new character, you significantly increase the population of AST. And so if you introduce new operator, you will once again increase more this population of AST.
Okay, thank you.
And just a small remark. But it's related to what Maxime explained, so it's not directly a question asked by the audience. You have to understand that in this work there are 2 contributions. So there is the exploration phase, the growing phase, as said François, where you try to discover new ASTs and the objective function. But actually, you could use the objective function that you want. And some other works tries to optimize the AST differently by, for example, counting the number of each operators, and each kind of operator has a given price. And so you could weight each AST using this kind of objective function. So it's up to you. If you want to change your objective function because you are not convinced by the one we propose, you could plug another one.
There was a question also online first by
Matthew Andrews, you can speak.
Hi, thank you. Actually, my question, well, I have two questions. My first one is also appeared in the chat, which is, can you explain what happened with the 5% that were unsuccessful? Is that a function of the local search in the sense that you can make some decisions that actually prevent you from matching later examples? So is it somehow an inability to kind of back up and deal with later examples because of earlier decisions? So that was my question one. My question two is also on this figure. When for the green dots, when you're better, is that just better related to your objective function, or would a human also look at your regular expression and say that's better? Or for those examples, would you look at them and actually say, well, actually, I see why it's not as good as the original regular expression? So I'm just wondering, in the green dots, are they truly better? So my first question is, what happened to the 5% unsolved? And secondly, would a human say that the regular expression in green was better than the original one?
So for question one, the unsolved happened mainly because of since it's a search algorithm, we're building the solution using an incremental process. And what happens is sometimes the combinatorial explosion happens somehow too early in a way, and the algorithm gets clogged, like stuck in the earlier stages. So even if the system of priority queue is designed so that the search will be done both in width and in depth, it still somehow gets stuck and it doesn't manage to process enough ASTs to go deep enough to find at least a good solution. So it's not often, but in about 5% of the ones we have, it happens. And from what I remember, it was mainly the long instances. So the regular expression which produced long words on which it happened, because it means longer problems to solve somehow. For question two, for the green dots, sometimes it's due to the fact that our objective function would advantage too much shortness, for instance. So it finds some of a trivial regular expression. But most of the cases come from the fact that the regular expression we generate are random. So even if we have some simplification rules that we apply to prevent having A or A, for instance, if we have A or A, we will just simplify it into A, and some simplification processes like that. They still sometimes can be simplified. For instance, if I have AB or AC, maybe I want A dot B or C. So in most of the cases, they were truly better because the randomly generated were sometimes not very well made.
Okay, that's clear. Thank you.
There was a question also here in the room. No, okay. It was already answered. Other questions in the room?
I think there was another question on the bridge.
It was yeah.
I have several questions and suggestions. First, I have a very naive remark, which is that, as you mentioned yourself, when you have a bunch of examples, you always have several trivial solutions at your disposal, which are putting an or on all the examples themselves. So exhaustive description of the example, which is a matching regular expression, and the other one being just saying, okay, do whatever you want with the alphabet that we are using. So in the case where you don't manage to find a good AST, you could just return one of those ones just to remove the 5% of unsolved, and ensuring that your algorithm will really be an anytime algorithm, in the sense that you are always able to return a working result. That, yeah, it's very naive. I also, maybe I was wondering also, since these are examples that always work, would it be interesting to try to include them in your priority queue as examples that can also be mutated to be improved, or you see what I mean?
No, I don't think that would help too much. For one, for the case of the regular expression that recognizes only the examples and nothing else, it wouldn't help because the AST is massive already. And all the mutations always add nodes. They never take something away from the AST. They always make it bigger. So it wouldn't help so much. And for the other one, the same problem would happen. The mutations never make a language smaller.
Okay.
Almost all of them make that the language will become strictly bigger or the same size, way of saying.
And actually, this is how you guarantee that when you do mutation, your AST are backward compatible.
Yeah, sure. Yeah, sure.
Yeah.
And another question, can you go back on the formula for the objective function f? So yeah, as far as I understand, each time you're testing a new AST, you will compute this objective function for the AST, and so in that in here there is an infinite sum over something combinatorial. And how costly is it to compute that objective function?
It's the most costly part of the algorithm by far.
Exponentially, or do you have? Are there clever things that make it not exponential?
No, it's not exponential. Wait, in theory, it's exponential, but not in practice. What we are doing is we are transforming the AST into an automaton.
Okay.
That automaton, we determinize and minimize it. That's where there's some fake exponential, like in theory it's exponential, but in practice it's not. And from a minimal and determinist automaton, we can have some clever tricks to count not to the infinity, but far enough that that the amounts we're adding become negligible. Because what's on the bottom here, size of sigma to the k, grows so big that after some terms, the quantities become negligible.
Yeah, anyway, it's bounded by the sum of the beta k from where you are to the infinity.
Yeah, and it becomes so negligible that basically we count to 30 and we stop.
Okay.
Because, and beta k also, beta k is the positive series. So beta k and sigma to the k in our experiment, after 30, it would be 6 to the 30. And that's a value that will become negligible very quickly.